Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at pressure increase operations for Design 1. And we're doing heuristics both from the textbook by Turton et al. As well as the one by Sider and Cedar and those guys. So first let's look briefly at pumps and compressors. So in our textbook, we have a table 11.9 as heuristics for pumps. And so probably a lot of details about a pump that you've not thought about yet. And we'll be looking at these in more detail later. But these are some of the things that you may need to know would be typical values. And what type of pump, centrifugal or axial or rotary, reciprocating, etc. And so different guidelines for those. And then we also have one for compressors, fans, blowers, and then also vacuum pumps is included in the same list. So fans and blowers and compressors all sort of mentally get very confused and muddled in people's minds. In some respects, they're very similar because they're used to move gases. Usually a fan is going to be used if you are really not caring too much about increasing the pressure. Okay, it'll only increase the pressure about 3%. And a blower can increase the pressure a little bit higher. But if you need something even higher than that, then you're going to want to use a compressor. Okay, now again, blowers and compressors frequently get kind of muddled in the literature when you're looking on data for those. There are all sorts of guidelines here about what kinds of expectations you can have for inlet and outlet. And remember that generally we don't want to compress to more than about 3 times the feed pressure in any one stage. So out of Sider's book, we have some guidelines on how to make decisions. So use a fan to raise the gas pressure from atmospheric pressure up to maybe 10 kilopascals. Okay, use a blower or compressor if you're wanting to raise it higher than that. And if you need to go to even higher pressures, then you can either use a compressor or stages in a compressor. So a staged compressor system. We'll need to estimate the theoretical adiabatic horsepower. And this formula here tells us how to do that. Now remember that SCFM is standard cubic feet per minute of a gas at standard conditions. It is equivalent to a molar flow rate more than it is to any volume that you actually would measure out in the field. Okay, temperatures and pressures here need to be in absolute. And most of the time we are able to assume that reasonably close to ideal gas behavior is going to be true for our gases that we're treating. You can estimate the number of gas compression stages, and this table here gives you a way of doing that. And then the optimal interstage pressure is going to correspond to the horsepower for the compressor. So you're going to figure out what that is, and then for each stage you'll have an intercooler, and then that'll probably drop the pressure a little bit, 2 psi, 15 kilopascals, something in that range. If the head is up to 3,200 feet and the flow rates are in the range of 10 to 5,000 gallons per minute, on a pump you want to use a centrifugal pump. They're going to be the least expensive option and most reliable for operations. For higher heads, you're going to want to use a reciprocating pump. Those are the type that you see, for instance, I'm from Oklahoma, so driving across the plains in Oklahoma, you frequently see reciprocating pumps. There are also axial pumps or rotary pumps, and those have appropriate applications also. When you're talking about liquid flow, you need to assume that there's going to be a pipeline pressure drop of about 2 psi for every 100 feet of pipe. And a control valve will have a pressure drop of at least 10 psi. That's going to be important in figuring out how much pressure head you need at the outlet to your pump. For every 10-foot rise in elevation, you should assume a pressure drop of 4 psi. Now you want to estimate the theoretical horsepower for pumping a liquid using this formula. Okay, these are in English or American engineering units. If you want to drop the pressure, well, you can use an expander to reduce the pressure of a gas, but you can also use a pressure recovery turbine to reduce the pressure. Okay? You're going to do these things when the pressure drop is enough that you can actually get an economically reasonable recovery of energy. So 20 to 150 horsepower for the gas or for the liquid. Again, we have formulas for how to estimate what that theoretical horsepower would be for a liquid. And then you want to decide whether or not you are going to, how are you going to move a fluid from device 1 to device 2? And the question really becomes, should you pump a liquid or should you compress a gas to get it between the two? Generally, if you're trying to increase the pressure of a stream, you are going to spend a lot less money pumping a liquid rather than compressing a gas. The exception for that is if it's going to require refrigeration in order to get that liquid. So if you have a vapor that you need to move, it is most of the time much less expensive to add a condenser, a pump for a liquid, and then you can evaporate it again back to the gas phase if necessary. That is typically less expensive than just doing a compressor for a vapor. Okay? Now there is an exception. If those condensers require refrigeration, then you need to do a more complete economic analysis. Now, vacuums probably are the thing that we have studied least so far in our curriculum. One problem of a vacuum system is it always has some in leakage. So you're always they're never going to be as leak-proof as a pressurized system. And so there are formulas for estimating how much we should expect, and this is one that's recommended. If you want to reduce the amount of gas sent to the vacuum system, it depends on what the temperature is. So if the temperature is greater than 100, add a condenser with cooling water before the vacuum system. But if it's going to be lower temperatures, then you can just, send it straight to the vacuum pressure. For pressures down to 10 torr and a gas flow rate up to 10,000 cubic feet per minute, at the inlet to the vacuum system, you're going to use a liquid ring vacuum pump. For pressures down to 2 torr and higher gas flow rates, you're going to use a steam jet ejector system. And you can have this staged with direct contact condensers between the stages. If you have a 3-stage steam jet ejector system, you can use that to achieve a vacuum of 2 torr, 100 pounds, or 100 psig of steam per pound of gas. If you need to move solids, well, if the solid particles are small in size and have a low particle density and aren't sticky, okay, then pneumatics, so just blowing them with air through a pipeline can work very well. But if it's sticky or abrasive or if, heavy, you'll probably want to use a screw conveyor or a bucket elevator, depending on the physical setup. For solid particles of any size and shape that are not sticky, you can use a belt conveyor, and the incline on that belt conveyor can be up to 30 degrees, and you can make those quite long. These things can be a mile long if you need to. If you have a process where you are needing to change solid particle size or separate solids, we have crushing concerns. So jaw crushers, gyratory crushers, cone crushers are the ones that are used. If you're needing to grind to fine solids, for instance, I do this every day with my coffee. You're going to use a rod mill or a ball mill. Particle size enlargement, I'm going to want to compress my powders or my granules. I can do rotary compression. I can do extruders, roll compactors, rotating drums, rotary discs, various varieties of binding small particles together. And the size separation of the particles, there are ways that we can do that. So essentially, you're doing a sieve type operation. And these are going to be a variety of different techniques, so perforated screens, inclined woven screens, etc. A cyclone separator can be used to remove solids from a gas. Or actually, you can do this for a liquid also. It will still have entrained liquid with the solids, however. And then finally, a quick look at the entire flow sheet, some things that you need to think through. First, you want to increase your second law efficiency. Remember, we need to be good stewards of our environment, and we want to reduce energy consumption. One way to be the best steward is to avoid mixing streams with different temperatures, very different pressures, or different composition. If it's a new process, we want to determine how it differs from the similar conventional processes and figure out what those advantages and disadvantages are. And then if you find disadvantages, figure out if there's a way to maybe change that part of it. Also, when you're looking at new processes, figure out the maximum production rate and yield and look for ways that you can increase those. You want to calculate theoretical efficiencies by using lost work analysis and find ways to increase that. Another thing, process intensification is a huge topic these days. We want to carefully examine our process flow sheet, looking for ways that we can eliminate equipment by combining steps, rearranging things, or replacing process steps. One that's very common is doing reactive distillation. Instead of a separate reactor and distillation column, combine those. But there are many other ways of doing process intensification. And then finally, perform preliminary economic evaluations at different production rates and look at the plant sizes. So once you've started looking at your equipment, look and see whether or not it might be more economical to go to a larger size or maybe a smaller size, because the size of the equipment actually can make a difference in the economic analysis. So this concludes our study of heuristics, and next we'll look at more careful design of various components of our system. Thank you very much for your time.